Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue thinking about streams and flooding. In this video we're going to be looking at how do river systems change downstream, and this is going to correspond to section 16.3 of your textbook. So if we look in front of us here, you can see that we have a diagram, and this diagram is showing us the changing gradient that we expect to see with a standard river system. So typically we know that the source of our river is very often going to be located in areas of elevated topography, typically mountainous areas or hilly areas. Now this isn't for every river, but the vast majority of them will start in higher ground. Now as we progress from the river's source up here in this elevated terrain to the river's mouth down here, we can see that there is a steady change in gradient. So to begin with, we need to define what gradient is. So the gradient is defined as a change in elevation over a given horizontal distance. So you can see on this diagram we have three separate locations selected, segments 1, 2 and 3. And you can see that for each of these locations we are using a 1 kilometer horizontal distance. And you can see that's consistent between 1, 2 and 3. Now what you'll notice though is that over this 1 kilometer distance there is variation in the vertical change. So we can see that in segment 1 for 1 kilometer of travel the ground surface drops by 15 meters. In the case of segment 2 for 1 kilometer horizontally the ground surface drops by 8 meters, and for segment 3 for 1 kilometer's horizontal distance the segment drops by 4 meters. So what you can see is that there is a steady changing gradient. So the gradient up in segment 1 is going to be the highest, and the gradient down here in segment 3 is going to be the lowest. So the question then becomes, well, why is that important? Well, typically the faster your water is dropping, the more energy it's going to have. Now straight away you're going to be thinking, right, more energy must therefore equal more velocity, but that's not actually correct, and we're going to discuss that in the next slide, so just bear that in mind right now. Now when we're discussing gradients, it's normally expressed in the form of meters per kilometer or feet per mile. So for instance, in the case of segment 1 we have essentially a horizontal distance of 1 kilometer and a vertical drop of 15 meters. So that would be the equivalent of 15 meters per kilometer. That would be our gradient. Now typically the steeper the gradient, it will cause the stream to drop more for a given distance. As I said, this will typically impart more energy into the water because it's dropping under gravity faster. Typically by the time we're down here in segment 3, the energy of the river will be lower because the water will be dropping more slowly. Now as I said, this doesn't necessarily mean that the water in your river will be flowing faster in segment 1 than segment 3. What it does mean is that the water moving in segment 1 will have more energy, and this will mean that the water moving in segment 1 will have the capacity to move larger class sizes. So the water up here can move things like clay, silt, sand, but also the larger class sizes, gravels, cobbles, boulders. In contrast, the water down here in segment 3 is going to be moving far more slowly, so it won't have the capacity to move the larger class sizes. So down here, the water will probably only be able to move clays, silts, and maybe sands. So how does our river system actually change downstream? So you can see here we have a diagram of a river system. You can actually see the main channel itself is starting about here, so that's the source of the main channel, and you can see the main channel is coming round and down like so, and it's emptying into a body of water here. Could be a sea, could be an ocean, could be a lake. So you can see this diagram has been labelled. We have H, essentially that represents the headwaters for our river. That's essentially the river source. We also have T1, T2 and T3. These represent the locations where we have tributaries entering our main channel. So if you remember, the tributary is going to add additional water and additional sediment into our main channel. So every time we add a tributary, the volume of water in our river should increase. Down here at D we have ourselves a delta, and deltas are going to form when our river enters a body of water which is more or less stationary, because as our river enters that body of water it causes the velocity of the water and therefore the energy of the water to suddenly decrease very, very quickly. And so this means the water loses energy, and so it naturally has to start depositing sediments. And so when our river enters a body of still water, like a lake or an ocean for instance, it's not uncommon for a delta to form as the river water stops, slows down and has to deposit sediment. Then finally, once the sediment's been deposited, the water will continue across the delta and then it will enter into the body of water proper, and that's going to be the mouth of our river. So I hope that covers all the basic labels which we can see on this diagram here. So we're going to look at some of the changes now that will be taking place as we progress from the headwater to our river's mouth. Okay, so the first one's not really going to be much of a surprise. It's all to do with the channel size. Well, we know that up here in the headwaters, there's actually not going to be that much water in our river channel, and so our channel is on the whole going to be very, very small. You think of it like a mountain stream, for instance, not a particularly big channel. Now, as we progress down towards the mouth, we can see we're going to have more and more water being added to the main channel. So all of these tributaries are all contributing water into the main channel, so that means the volume of water in the main channel is going to keep getting larger and larger and larger. And you can see that at T1 here, which is the first major tributary entering the main channel, you can see that after T1 there's a noticeable increase in the channel size. After T2 another increase, after T3 another increase. So each of these increases are associated with additional water being added to the main channel from our free tributaries. So this isn't a huge surprise. And so because we have more water, our channel obviously has to increase in size to accommodate the extra water. And so this means our channel will become wider and deeper as a result. So this isn't a particularly unexpected change. So the next change we need to think about is water velocity. Now, as we were just discussing, up here in the headwaters where we have a steeper gradient, the water is going to be dropping faster, and this means the water is going to have more energy, so it can move large clasts. However, it doesn't necessarily mean our water is going to have greater velocity. So the reason for this is that as the amount of water in the channel increases, it will typically mean the water will flow more smoothly. And smooth flowing water will be capable of greater velocities. Up here in this area of elevated terrain, we're going to have a situation where yes, our water is moving with a lot of energy, but we have less water in our river channel. We have more obstacles in our river channels, so there's more stuff for the water to flow around, and typically because there are more obstacles it also means there's going to be greater drag on our water. And so it means that even though this area towards the headwaters is going to have more energy in the water, it doesn't mean the water will flow faster. Typically the water will actually be flowing at its quickest in the more gentle portion of the main channel down here towards the delta. That's when you're going to have the maximum amount of water in your channel. By this point your channel will typically have quite smooth margins, and the greater volume of water will typically allow for a more smoother, less turbulent flow. And so this means your water will actually be moving faster than it would be compared to this area up here towards the headwaters. So the next thing you need to think about is discharge. So discharge, if you remember, is simply the area of a river channel at a given point multiplied by the water's velocity. So we know that as we progress from the headwaters to the mouth of our river, the channel size is increasing. We also know that as we progress from the headwaters towards the mouth of our river, the water velocity is also increasing. And so the channel's getting bigger, the velocity is getting bigger, and so as we progress from the headwaters towards the delta and the mouth of our river system, it means obviously the discharge is going to get higher, because once again, discharge is simply the channel size, the channel area, multiplied by the velocity. And you can see that as we go downhill, both of these values are getting larger, so the discharge will do the same. The next factor is the total stream load, and this is going to be a reflection of how much sediment is being moved by our river. So once again, this is going to be a reflection of the amount of water in our river channel. Typically, the more water you have in your river channel, the more sediment you can move. So even though, once again, up here in our headwaters we have a river, it's going to have lots of energy, so it can move a very broad range of class sizes, everything from clay all the way up to boulders. It has the problem that there actually isn't that much water in the river channel itself, and so it can't actually move that much sediment, even though the water that is there has a lot of energy. In contrast, by the time we're down here towards the end of our river, the amount of water in our channel has substantially increased, and so this means it can move substantially more sediment. And so over time, as the amount of water in the channel gets higher, so does the total stream load. Now, there will be a change in the classed sizes that are being transported, and we'll discuss that in just a second. Now, as we discussed earlier, as our river heads into our delta area, we have a sudden decrease in the velocity and energy of our river. And so this means at area D here, as our river begins to move across our delta, the water slows down, and so it has to start depositing sediment. So you'll notice that the sediment load is steadily increasing, but when it hits the delta, the stream sediment load drops. And this is because the water is decelerating, losing energy. It has to deposit sediment. And so this means by the mouth of our river water is actually only transporting a relatively small amount of sediment, and most of that sediment will be the finest material, so it will tend to be a clay-sized clast. The final thing that will change as we progress from the headwaters to our river mouth is the maximum sediment grain size, so how big are the clasts. Now, this does tie back to the amount of energy that our river water has, and of course that is a reflection of the gradient. So up here, where we have higher gradients, the water is dropping faster, so it has more energy, so it can move larger class sizes. So it can move everything from clays all the way up to boulders. Now, as we progress downstream, the gradient steadily gets lower, and so this means by the time we're down, let's say around T2 and T3, so in this area here, the gradient has shallowed. That means the river has less energy, and therefore it will become incapable of transporting larger class sizes. So by this region here, it won't be moving boulders, it won't be moving cobbles, and it won't be moving pebbles, because they're just too big to be moved by the water. It just doesn't have enough energy to move them. So they will have been deposited further upstream. By this point, though, it still has sufficient energy to transport class, let's say, such as sand, silt and clay. Now, by the time that we move further downstream, the gradient keeps getting lower, and so as the gradient gets lower, the water becomes less energetic, and so we start to get smaller and smaller class sizes being moved by the water, and larger class sizes are being deposited. So by the time we're down here in the delta, we have a situation where we're moving only the finest material. So we're moving clays, silts, and maybe fine sands, because that's all the water has the energy to move. It can't move big stuff like boulders, cobbles, and gravel, because it's simply not energetic enough. Obviously, by the time we hit the mouth of the river, the water comes to a near complete stop as it exits the delta and goes into the larger body of water. And so at this point, the grain size typically becomes very, very small clay, or no sediment left whatsoever. So you can see that our river system undergoes these 5 major changes as it progresses from the headwaters to the river mouth. So the next thing we need to think about is how sediment size, or the transportation of sediment, is affected by the current velocity, so how quickly the water in our river is moving. So what we can see on this diagram is, you can see down here on the lower axis, we have 3 different sizes of sedimentary clast. We have clays and silts over here on the left, sands in the middle, and gravels on the right. On the vertical axis here, we have velocity in centimeters a second. So you can see we have 0, so no velocity, 10, 100, 1000. So velocity is increasing as we go up. We also have 3 regions on our diagram showing us how the sediment is being transported in each region, or whether it's being deposited. So below this blue line here, this means the velocity of the water is so low that sediment must be deposited. In this region here, the velocity of the river is fast enough to transport sediment, but it's not fast enough to pick up and suspend that sediment in the water, so it has to be moved as part of the river's bed load. And in this area up here, the water is moving fast enough to essentially pick sediment up, suspend it within the river water and transport it in the form of suspended sediment. And so we can see that as the velocity changes, it's going to affect how the sediment is transported and also what size of class our river water will be capable of moving. So if we look here, we can see at high velocities, our water has the capacity to move small particles and sand. So up here, let's say around 100 centimeters a second, we can see that silt and clay will be moved in suspension within the river water. We can see that smaller sand-sized clasts will also be picked up and transported in suspension in the river water. But we can see that medium and large-sized sand clasts will not be picked up by the water. They will instead be rolled along by the river water as part of the bed load. We can also see that at 100 centimeters a second, gravel-sized clasts will also be rolled along as part of the bed load by the river water. So at moderate velocity, so let's say 10 centimeters a second, we can see that we have a change in how the sediment is being transported. So we can see by this point at 10 centimeters a second, the river only has enough energy to transport silt and clay-sized clasts in suspension, so held within the river water. We can also see that at 10 centimeters a second, the sands are now being transported as part of the bed load. They're no longer being picked up by the river water because the river water no longer has sufficient energy to pick them up and transport them that way. We can also see that at this point, larger sized sand clasts and gravel cannot be moved by the river. They must therefore be deposited at this point because the river no longer has sufficient energy to move them. Now, once we get to very, very low energy, so we're down here, let's say around the 1 or 2 centimeters a second, we can see that we can still move silt and clay as part of the suspended load within the river water. And so this shows us straight away that in order to deposit these very, very fine class sizes, your water needs to be near stationary. It almost has to come to a near complete stop. Now, by the time we're down at these low velocities, your river water will no longer have sufficient energy to transport sand-sized clasts or gravel-sized clasts, so they will have to have been deposited by this point. So we can see how the change in the velocity of our river is going to have a direct effect on the size of sediment which is being moved or deposited. And of course this is replicated or is shown in the types of sediment which are being deposited and therefore the types of sedimentary rock that form. And so as geologists, we're very, very interested in this particular side of river transport because it tells us a lot about the river and how it's moving its sediment and what speeds it may have been going at. So the final thing we need to think about is how does a stream vary over time? So we have another hydrograph here, and in this case you can see we have discharge on the vertical axis, and across the horizontal axis we have the 4 seasons: winter, spring, summer and fall. And you will notice that throughout the year the discharge does change. So why is this? Well, in the winter, we typically have the lowest discharge. I should point out, by the way, that this particular diagram here is for an idealized river system. It doesn't necessarily apply to all areas of the world. So, for instance, this particular diagram would not be representative of an area such as Houston, because as we know, in Houston, in Texas, we tend to have relatively warm winters, so we tend to have quite a bit of precipitation in the winter, the spring, and we tend to get our highest rates of precipitation during the summer, where we have very, very strong summer thunderstorms. So don't think that this particular hydrograph is representative of all rivers. Right, let's get back to it. So in the winter, in an idealized system, we tend to have the lowest rates of precipitation. That's for a couple of reasons. Or should I say the lowest discharge? That's for a couple of reasons. Number one, during the winter, precipitation actually decreases because the cold weather actually inhibits the formation of raindrops and ice crystals in the atmosphere if the temperature gets low enough. We also have a situation where if the temperature is low enough, the rain will instead fall in the form of ice or snow. And so this will mean the water gets locked up in the ice and snow, and so it doesn't actually get released until the ice or snow melts. And so this means that typically during the winter we have lower rates of precipitation, and we will often have water being locked up in the form of solid water in the form of ice and snow, and this stops the water entering the river system, and so the discharge is often at its lowest. Now, as we head into spring, the ice and snow that's been gathering in the winter will begin to melt, and so we see the highest discharge, or the peak discharge for the year, will typically occur within the spring months. And this is simply a reflection of, number one, the melting ice and snow, and number two, the fact that as the climate begins to get a little bit warmer going into the spring, this will typically bring about slightly more chaotic weather patterns, and so this will often lead to higher rates of precipitation, so more rain. Now, as we pass through mid-spring and start heading into the summer, we typically begin to see the discharge dropping off, and this is because the weather systems begin to become more established and a little less chaotic. And so as the weather systems begin to become more established and stable, we see a bit less precipitation falling, so we see the discharge beginning to drop. And so we know this occurs because typically during the summer months, the rate of precipitation will often decrease. And this is because there's, the atmosphere has become less chaotic, and essentially a less chaotic atmosphere typically means less change in weather, so fewer weather systems passing through, which will deposit things like rain as they move through the area. Now, in the summer, what we do have, especially during the midsummer, is we tend to have higher temperatures, and this can lead to rather strong summer thunderstorms. And so it's not uncommon during the midsummer for the discharge to increase, typically due to the introduction of water from several large, relatively short-lived thunderstorm events. Now, as we progress out of the summer, once again, we tend to see a decrease in discharge, and then we see an increase in discharge as we head into the fall. And this is because we're moving back into a period of more intermediate temperatures, more changeable conditions, and so this is going to create a more chaotic atmosphere, and so this is going to be reflected in more chaotic weather patterns and more precipitation falling. And then, as you can see, the discharge begins to decrease again because we're heading into the winter months, and conditions obviously are becoming less and less conducive for water entering our river system. All right, thank you for watching, everybody, and have a good day.